So yeah, thanks again for the invite, and yeah, you set the bar very high to start this talk. But yeah, what I actually like to do today is give you a bit of broader overview of what I'm doing in my lab on learned database components, which contains the work that I presented at CIDR, but also goes over some other directions. And the principal theme is, so when this line of learned components started, we saw one weakness that I will cover in the talk, and we try to think about how can we work around this weakness of very high training overheads of learned components. And all this work that I'm presenting today, so the main PhD student behind actually all the work that I'm covering today is Benjamin. He's here on the slide, and I'm also working with some other colleagues in Darmstadt, especially the second from the right is Christian, my machine learning colleague, with whom I'm having actually intensive discussions on this topic. So he got quite interested in this line of work, and I think here this exchange between these two domains actually helps to us to how we should think about how we can apply machine learning in the area of databases. Good. So before I actually start and talk, let me bring everybody in the same page. What do I mean when I talk about learned DBMS components? So the basic idea of learned DBMS components is that you replace a classical component, such as an index, for example, a B-tree, with a machine learning model. You might argue, why should you do that? And so recent papers have here shown that this approach has actually high potentials, because learned components can, on the one hand side, improve over complex classical components, for example, not only index, but also an optimizer, since they are able to capture, for example, better data correlations or complex data distributions than maybe simple analytical methods or heuristics that we are using in database systems. And on the other side, if you think about learning, what it also gives you, if you can learn from a behavior, you can reduce the manual engineering effort. So if you just train a model by having some training data that tells you how an optimizer should behave, you get rid of this manual engineering effort that is often needed to implement these complex components. So in the best case, it saves you significantly manual engineering costs. So another observation that maybe renders learned components interesting is the observation that learned components in the recent past have not only been used for indexes, but actually by now there is a wide spectrum of papers that covers, I would say, almost any database component you can think of. Could be indexes, but it also could be learned operators. So for example, learned sort operators were presented in one of the database conferences, but also going more towards the optimization side. So learned cost models, learned optimizers, learned query schedulers, etc. pp. So it means it has been shown that so learned components have a really wide applicability and have been successfully used for these various different database components. So the question is, so what is wrong with these components? And this is what I'd like to cover in the next few slides. So where currently one of the main weak points is, there are many more that actually would need to be covered to integrate those learned components into real system. And to better understand where the main pain point actually, or where I see the main pain point, let me quickly go over how the state of the art realizes learned components. And this is what we coin learned components or database components 1.0. So the predominant approach here is what we call workload-driven learning. And to understand what workload-driven learning does, let me use a quick, simple example of a learned component that tries to estimate query runtime. So we want to look into the question, how can we use a machine learning model to implement such a learned query runtime prediction? So how this works with workload-driven learning in a nutshell is that you first need to collect a large training data set for your given database at hand. So for the set of tables that are filled with tuples, you run a set of queries, and then for those queries, you just observe the runtimes that you want to predict later on, and then feed this as training data into your whatever model you're using for the prediction task. And at runtime, once you train such a model, you just use the very same model for the very same database to predict the runtime for new queries. So you need to featureize or represent these queries clearly for machine learning models such that it can do the prediction, but the idea is that the model learns kind of the complexity of different queries and thus can capture what it means for the overall runtime. So what is wrong with this approach? It's wrong that, or what is the main pain point? The main pain point is that this is highly unattractive in practice. Then the learning and the training costs for this are pretty high. And if you look at the example before or other papers that have been published, you see very often, if you read the papers, that they use tens of thousands or even more training queries to train just a single model. And here the problem is not training the model, but just collecting this large training data set on potentially large databases, which might cost you hours or days to execute before you actually have your queries, query plans, and the runtimes that you are predicting or that you want to predict. And the second point is that this is not a one-time effort. So meaning training data collection needs to be repeated for every new database. So when a new data set, a new set of tables comes around with different data characteristics, you need to run 10,000s of queries. Or even if the data in the same database changes, you need to adjust for potential data distribution shifts, meaning you need to again collect training data for at least a subset of tables that have been updated, or if other queries are joining with these tables, which means again high overhead, and before you can actually use your model again for example, for query runtime prediction. And maybe one point that I don't have here on the slide is today you need one model per task that you are doing. So this is all multiplied by the number of tasks in your database system. So you would train a different model for maybe query scheduler than other than for your query optimizer, while maybe some components in these models could be shared. So what is the vision that I'm trying to kind of push forward in my lab? And the vision of this, what is also the title of my talk, so Learn Database Components 2.0, is actually make these high costs and the inflexibility of workload-driven learning go away. So the question is, can we learn such learn components, train such learn components with much lower overhead, and maybe even reuse one model for different components in a database system? And today I'd like to cover two directions that we propose that we think, which is not a particular, let's say, approach for just one model. It's more like general schemes how you would train a model. And these two directions we think are possible to cover actually really wide spectrum of different components. And why we need two directions and then one, I'm covering this in my talk. But the basic idea is with those directions, you can bring down the training costs very significantly. And the first direction is a paper based on several papers we published in the past, but mainly on a paper from VLDB 20, where we proposed a direction of so-called data-driven learning. And the idea here is that with this learning scheme, we can learn a model from data without actually running any workload. So the idea is that the model captures the complex data distributions in your relational database within tables or across tables, and then you can use this model for several database tasks, for example, cardinality estimation, but we've also shown that you can use data-driven learning approaches for other tasks like indexing, or even maybe not core database tasks, but data-related tasks such as data cleaning. But this direction that only has information about data is clearly limited to what it can be used for, because it has no notion of query complexity and what it means to execute queries. So to cover tasks or database components that inherently rely on the notion of query complexity, or need to capture that in the model to make decisions, for this direction, we propose another, for this problems, we propose another direction that we call zero-shot learning for database management systems, which also, again, the idea is we need to bring down the high cost of training data collection. And here the main idea that is behind that we rely on the idea of so-called pre-trained models. So for example, we would train an optimizer across several databases and can then just use it out of the box for a new database where we either directly can use this model without any training overhead by simply just doing some fine-tuning of the model. And the interesting thing, these two things kind of interdepend on each other. So what we do on data-driven learning can actually inform decisions what zero-shot models would do. So for example, if you have zero-shot optimizer, you can couple it with a data-driven model and that way allow a zero-shot optimizer to actually perform out of the box on an unseen database. So let me now go over these two directions in the next. I'm not sure how long I have. Please stop me if it's going too long. But I try to cover both the basic ideas and some details of our approaches for both directions. So let me start first with this direction of data-driven learning. So the basic idea here is, as I said before, that the model learns the multivariate data distribution over a complex relational database, meaning across attributes and across tables. So the basic idea here is that you use a model, class of models that I'll introduce later on, that first, if the data is back, samples a representative set of this database, and then a model is trained on the sample to learn the multivariate data distribution in an accurate manner. And at inference time, you use these data-driven models for different tasks, for example, for cardinality estimation. And the benefits which are implied from what I said before are you don't need to run any training workloads, meaning these hours and potential days of training data collection go away. Another nice thing is based on the architecture we've chosen, and this is more particular, so how we modeled this problem, is that the models are directly updatable in our case, meaning if you have an update or an insert in your database, you even don't need to retrain the model with the new data sets, but we can ingest the data similar to like updating an index into our models, and I'll show you later on how that works. And at the end, the nice thing about the models we are actually using, and I'm showing later on, is that they can support multiple tasks with the same model. For example, cardinality estimation and a form of approximate query processing. So answering queries quickly in an approximate manner can be done on the same model architecture. So I guess you don't need to spend too much time, but again, to bring everybody on the same page, what is the cardinality estimation problem? So if you have a query like that joins three tables, customer orders and order line, you have different selections, filters on the different tables. The first task, or one of the main tasks, the database system and the optimizer has to solve is find an optimal join order for the plan, and this depends on the cardinalities that a particular plan or join order has. So the task to come up or to decide if a plan is actually good or not is what you need to do is first derive these intermediate cardinalities. Assume in this case it's 5 million, 10 million for one plan, and for the other join order it would be like that. And in this case, you can kind of infer the second join order is better. The question is now, clearly, we need to do this without executing the query, so this needs to be predicted, and this is what the bread and butter of a database optimizer is, to provide estimation methods for these intermediate result sizes. So while classically, this is a problem where no learning has been used. Recently, there was a paper that was actually, I think, originally also presented at CIDR in 2019 from Andreas Kipf, also TUM, now MIT, where he used a DNN to predict the cardinalities. And it uses this workload-driven approach that I've shown you before. So what they do is they enumerate different partial query plans, so meaning different join orders, and execute those queries to get the perfect intermediate cardinalities for these partial plans. And then they feed this information into a deep neural network that can do predictions. And as I said before, the downside is here they need to run a large number of training queries before the model actually can make so accurate predictions, but they've also shown that the model significantly outperforms classical techniques such as index-based join sampling or others. However, it comes at the price of high training costs that not are only one-time efforts but repeated efforts. So with our work, as I said, so we propose a new class of model that can completely avoid these workload execution phase, since we directly learn to estimate cardinalities based on the data characteristics across tables. And so what we actually do is, if you look at the right-hand side, if you have a given database with multiple tables, a naive approach would be that we learn one large RSPN across all tables, but this would be highly expensive because this means we would also need to pre-join these tables to train the model. And therefore, what we do actually in reality is that we learn an ensemble of RSPNs for the independent subsets of tables. So what we do is shown on the right-hand side. If you have this tiny example schema, we would, for example, learn an RSPN for the two tables custom and order, that can do cardinality estimation on those two tables, and then have two other RSPNs, for example. But splitting this, the large database in multiple models does not mean that we can only do cardinality estimates within these subsets, but we actually can do cardinality estimates for arbitrary joins. So even if the joins, for example, across several models, we can still support cardinality estimates in that case. And I'm showing you later how that works. To get the basic idea now, let me start with a single table case. So how do we learn an RSPN for one table? And for this, assume that we have a very simple table, example table as shown on the left-hand side here, the customer table, which also has only two columns in this case, the age and the region column. And we have kind of some, the data is dominated by some older European customers and maybe some younger Asian customers. And what the model actually learns is the structure of the data in a recursive manner. So it tries to identify kind of independent subsets of the data, meaning independent row sets, and then within these row sets, it tries to identify independent column subsets. So we split actually a table or a set of columns within this table if they are independent, which it allows us to learn actually very accurate statistics. So how would this work in this case? The model would be trained first by taking a table, then applying a classical clustering algorithm such as, for example, k-means, which clusters similar items together. And then within those clusters, we would then analyze if columns are independent. What the model looks like for if you split something in row clusters, we introduce a so-called sum node in the model at the top here, because we started just to build the model and address or annotate the weights on the edges that represent how much data falls into the individual clusters. Then, as a next step, as I said, we would within each cluster see which columns are independent or which column subsets are independent. In this case, assume now within each subset, age and region for simplicity are independent, meaning we would introduce a multiplication node. And then, since we are now at the finest granularity of columns, we would keep the statistics. So in the simplest case, a single dimensional histogram for each of these column subsets on the leaves of that model. But in general, this model can be recursive. So we would split further the table into smaller row clusters if we, for example, identify that columns are not independent. So you can think of it in the extreme case, if columns are highly correlated, we would split a table into individual tuples, and then by definition columns are independent. But to avoid that the model really grows that large, there are hyperparameters in the model where you can set a minimum cluster size. So if you reach this minimum cluster size, you would not split the row clusters into tinier pieces. But the model itself, it could be recursive, meaning you can stack these so summation and multiplication nodes in a model. So how can you use now such a model for cardinality estimation on a single table? So assume a query like this one here is given, where you want to know how many customers are from Europe and younger than 30. So we would push this down to the leaves, identify the fraction of tuples that qualifies for this query, then multiply on the multiplication nodes, and then do a weighted summation based on the weights of the summation And this gives you already then the fraction of customers from Europe, and then you need to multiply it with the size of the table, which gives you the cardinality estimate. So the question is now, this seems to be nice model architecture, but what happens if the data changes? And so in our paper, we've shown that we can actually use this like as a form of an index, or similar updated like an index, sorry. And that means when a new tuple arrives, we can do a top-down pass through the model and update the weights as well as potentially the histograms on the leaves if there is a new value that hasn't been captured before. So you could, in that example, if you insert a customer from Europe that is being 100, it would fall in the first cluster. We would push it down, update the weight of the clusters, and then push it down to the leaves, meaning that the distributions on the leaves might also change. And the same, you can do that for, could do that also for updates by using deletes and inserts. So if another tuple comes, we would do the next thing. We would adjust the weights accordingly for the next insert as well. Clearly, this doesn't capture shifts in data correlations. For example, if now finally there's a new correlation introduced by the new customers we insert, the model would still use the old structure. And if you detect data or shifts in which columns are correlated, you would need to retrain the structure of the model. So you would need to, again, build the structure from scratch. But there are solutions for that, because structure learning is an expensive task. Sorry. We could so people in machine learning have shown that you can use kind of a random tree structure and just initialize the weights accordingly, which would avoid you to recluster the data if, for example, such situations like data distribution or correlation shifts happen. Good. So one thing that I didn't cover yet is now, how do we scale this for database with multiple tables to allow us also to do, for example, cardinality estimates for joins. And the naive attempt would be that we learn one RSPN per join path we want to support. And then if we see such a query, would use the model that was learned for the particular join and then treat it as a single table case, as I've shown you before. But this is clearly maybe not the best case, because this doesn't really scale to large schematizers. And sometimes it's also, if you have cyclic schematizers, you would not be able to really enumerate all possible join paths at the end. So what we instead do in DeepDB is that, this is what I said at the beginning, we use such ensembles of RSPNs where we can combine different RSPNs if we need to do joins across multiple tables. So what we do is, given a schema, we look into what table subsets are independent. So here, for example, assume customer and order line are independent. So we would learn one RSPN for the first two tables and one for order line. And then at runtime, we can arbitrarily combine them, or even if we need to do cardinality estimation for only one table, let's say customers, we could also project the model to this one table. And we do this by using one technique, which we call tuple factors. And let me introduce tuple factors now by looking into this first case, where we have one large RSPN, let's say one for the customer order join, but we only want to know cardinalities for the customer table. It works similarly for the other case on the right-hand side, where you have two RSPNs that you want to combine, but I'm not covering this today. It's a bit more complicated. So the first case is just more intuitive to explain, but the same actually mechanism, so the tuple factors are used for that. So what is the idea? So here assume we have an RSPN built on this join for customers and orders. What this means that we, before we train it, we've computed the full outer join of the two tables, or the samples of these two tables. And what we also compute is these tuple factors. So for the first customer, it means, or for the first two rows, we have annotated that this customer has two orders. So it's one customer that has two orders. So what the model actually learns with these tuple factors is that given a customer with certain attributes, certain values, how many orders do they typically have? So it can, since it's just another attribute of a table, the model would learn to also predict these tuple factors. So you can kind of say, you learn the join distribution over tables. And so what we now have is a model that learned the full table and these tuple factors between the tables. And what we can do now with this, with such a model, in case we want to answer the cardinality for European customers only, what we would do is we would first of all clearly we can have the table size, which is here the size of the outer join, here meaning 5 tuples. What we can then do is use the RSPN to compute the what is the fraction of expected customers in Europe, because it's like in a single table case, it was built on this single table that represents the outer join. So you can ask the model, what is the expected fraction of tuples from Europe? And then we can ask the model also for the expected number of join partners that a customer from Europe has, which is these tuple factors. And since we need to normalize by that, you would just take the inverse of these expected tuple factors. So kind of reduce this by the typical join blow up that you get from joining a European customer with its orders. So what it means in this example, you have 5 tuples in this outer join, you multiply it with the expected number of customers from Europe, which would be 3 over 5, so which you would get from the RSPN. And you could also ask the RSPN how many orders does a typical European customer have. It would tell you 5 over 3, which is what the model learned. And then if you multiply it, you would see that this actually then computes the expected number of European customers, which is 2 in this case. Good. Coming to an end for this part here, and then to the second part. So we've used the DeepDB in our paper and compared it at that time to the learned baseline from Andreas Kipf, as well as other non-learned approaches. But by now, DeepDB, since we open sourced it, I think it has been used now in more than 20 papers as a baseline, and showed that we actually can consistently provide stable cardinality estimate across different data sets and query workloads. But let me show the original results. So we used it in the original result on the IMDb database and the job benchmark. So there's a subset actually of the job benchmark that I show here, which is job light. So it's more the simple workload, but we have also numbers for the more complex queries in more recent papers. And you see here the Q error, which is the error that the cardinality estimation makes. And 1 means good because Q error is a relative error. So factor 2 means like the cardinality estimates are factor 2 off. And you see, if you compare our approach to the approach from Andreas, as well as other approaches we used in the evaluation, like index-based join sampling or simply random sampling or whatever Postgres gave us, you could see that the cardinality estimates are even in the 95th percentile, not that bad compared to the other approaches. And also the question is, how well do we generalize compared to other learned approaches that need to see a workload? And here the problem is that you typically, the learned model, for example, in this case, has seen only 4-way joins with up to a certain number of query predicates, so 4-1 means here 4-way join, 1 predicate. For MSCSN, we trained it only, I guess, on 4-way joins up to 4 predicates. And what we used it for then in at testing time is 5-way joins or 6-way joins. And you see that if the MCSN goes beyond what it has seen during training, the estimates are getting pretty bad or are not that good as at the beginning, whereas we still can generalize to larger joins because we don't do this on a workload basis. We just do it on the data characteristics that we learn, and therefore we are kind of independent of the query complexity. Not really, because you still propagate errors, but it's much better than with a workload-driven approach. Yeah, that's what I already said. There have been many similar ideas now around that also do data-driven learning. They try to fix some of our problems, and there has been many follow-up work also trying to evaluate their approaches against our work. Data-driven learning, as I said at the beginning, is a more general paradigm and can solve different database tasks. In the DeepDB paper, we used it also for approximate query answering, but there's a ton of other tasks that you can do with a data-driven model, which I'm not showing in this talk, but if you're interested, we can chat, or the papers are out. But as I said at the beginning, data-driven learning is no silver bullet for all possible tasks, database tasks. Most importantly, if you need information about the complexity of workloads, so meaning query runtime or contention that is inherent to solve a task, then these data-driven models are not directly usable. And therefore, we propose this second direction that I presented at CIDR this year that we call zero-shot learning, where the idea is to have a pre-trained model that knows how to optimize, for example, queries across databases such that it can be used out of the box for a new database. So new set of tables and tuples. So the question is now, how does this work? The general idea, I already said it, is we train one model across several pre-trained databases, and then we take this or fine-tune it on an unseen database. And the question is here now clearly, so one of the main questions that I'm trying to show later on is, So first of all, how much pre-training is needed such that a zero-shot model can actually generalize to unseen databases, but also how would you design such a model architecture, because this is far from trivial. It's not a simple task, and I will also argue why. So coming up with the zero-shot model architecture is not trivial. So to understand a bit how zero-shot learning works, and so the task that we actually used at the beginning to see if it's feasible to follow that line of work or to enable this vision is, so we looked into the question, can we predict the runtime of a given query plan? So there's a database, a query plan given, and the model should give us back that the query takes approximately 310 seconds in this example. And we think it was a good starting point because this is a good task for a foundation that can be used for other tasks, for example, for physical query optimization, where you need to come up or decide which physical operator you want to use, but also for query planning, so scheduling, but also it could be used for design advisors. If you ask, for example, for a runtime of a query, if the index would exist, which is a bit a different form of the query runtime prediction, because you need to do this what if mode, what if an index exists. But actually, we've shown that this is maybe a direction where we can extend this work to. And today, this is again tackled by simple cost models, but also workload-driven learning has been used for this, but with the same downsides that I mentioned before. So the question is now, how do we enable zero-shot learning? And the first idea one might have, and we also thought about, is, so if we already have workload-driven models, right, that capture the complexity of workload, can we not just train a workload-driven models across multiple databases and then we are done? Because the model then learns from these different databases and we feed the new database and the query workload in, and voila, we have a zero-shot model. But this is not the case. And let me quickly explain why this is not the case. So it's not the case because the way how they model workload and databases is very much hard coding the model against one database. So for example, assume you want to build a runtime prediction model for the IMDb database. The first thing is you need to encode, for example, for your queries, which attributes are contained in the queries. In machine learning models, that is typically done by using some form of one-hot encoding. So we would have a large vector which contains an entry for each attribute of the schema. You would flag the attribute that is used, for example, in a, let's say, as a join predicate, and feed this in the model. So you can do this for a database, and people, this is the standard encoding that people are using. But think about the question now: what happens if I use the same mod or the same encoding for a different database? So, for example, take SSB. You would do the same thing again, right? Would represent your attributes by a vector and just flag which one is used in a query. But you can see here, if you just use it naively, then the same encoding in different databases has very different meaning. So you might be lucky because the vectors have different sizes. So you could, for example, train a model in IMDb and then use it in star schema benchmark, or further train it on the star schema benchmark. But the model would completely get confused because the same representations for attributes would have very different meanings. Now we could say, yeah, you can kind of concatenate the vectors and use different bit entries for each attribute, but then the model would not learn something that is generalizable, right? So because you would then just say for each, you have an entry for each attribute of a different database, so it cannot generalize really to a new database. So what the main message here is, there's no simple fix based on the model architectures that are being used today, because they can really be trained only on a single database. So what we instead therefore use is a new encoding of the information that we feed into a model. And since our task is now query runtime prediction, the question is, how can we encode a query in a way that it gets database independent? And let me quickly walk you through the idea. It looks a bit complex here on the slides, but let me go through it quickly. So the basic idea is we use a graph encoding. It's like that is something that people use in graph neural networks today. And the idea is we have one graph node for each type of operator or artifact that is in a query plan. So we have graph nodes for operators, as you see up here. We have graph nodes for query predicates that say, for example, two attributes are compared with an equal operator. but also for the scan, we use these graph nodes for attributes and tables that are being scanned, for example. But different from the models that we've seen before, we don't use kind of a encoding of the attributes, or which attributes are used that are kind of hard coding the semantics of one database into the model, but instead we use transferable features, meaning features that can be derived from any attribute. So for example, instead of saying we scan the table movie companies, we say we scan a table that has a certain number of pages on disk, if you think about a disk-based system. Or instead of saying we, let's say, need an attribute customer ID for the join, we would say the join attribute is an integer, and so on and so forth. So each of these nodes actually has features that we feed into the model that are database independent, or that you can derive from any database. Maybe one interesting thing to note is that we also feed in information from data-driven models. So this cardinality out feature that you see here is the output cardinality of an operator, which is a feature that we annotate to this plan, such that the model can learn. What we actually want to learn is based on these input features, what is the runtime complexity, and therefore the cardinality is an important information, and therefore we annotate cardinalities to such a plan, and they can come from a data-driven model, for example. So once you have such a annotated plan and the training data, for example, so assume you have several of these query plans across databases, so you know the runtime for each of this plan, you'll feed this into a graph neural network and then train it such that it can do runtime prediction on the top node of a query plan. What the training procedure does, without going into detail, it propagates all the information to the root node, so of the aggregate node. Then we have one additional model on the top that, based on this information that ends up on the root node, can predict the runtime. So the idea is that on the top node we have kind of embedding that captures the complexity of the whole query plan. And since we use database independent features, you can simply build up such a graph for a new database, plug in the characteristics of these new databases, so data types, relational table sizes, but also intermediate cardinalities, and the model can then predict the runtime. Let me now skip over the second part, so because I want to get to the results and also have some questions at the end. So here the question is, how much pre-trained databases do you need such that a zero-shot model can generalize? I'll skip that. If somebody has questions, I can go over that slide later on. So here's the result of our evaluation that we have. I think, I'm not sure if we covered that in a CIDR paper. We have now a full paper submission for this work. So the idea is here of the experiment. So we collected, for this example, 19 real-world databases with different sizes and different characteristics in number of tables and so on. Also, what domains and they come from, which might have an effect on the data distributions. So we collected 20 databases, and we trained on 19 real-world databases zero-shot model and estimated the runtime out of the box. So with a zero-shot model, that means the zero-shot model hasn't seen the 20th database. And here we compare zero-shot learning to what you get from Postgres. And you might say, why Postgres? So Postgres is a model that is a zero-shot model, right? So you don't need to, we didn't compare to other workload-driven models because they don't generalize, can be used out of the box for a new database. And this is what we wanted to show here. If you use a model or a prediction model for a new database out of the box, what is the quality? What is the accuracy? And we say scaled optimizer cost because what you get from Postgres is an artificial cost unit. We wanted to predict real runtime, so in milliseconds. So we used a simple linear model that actually translates the optimizer cost from Postgres to runtimes. This is much better than other papers who compared used Postgres costs for runtime prediction in their papers, because they often use just the cost units as directly as milliseconds, which doesn't make sense at all, and therefore they end up much higher QRS for Postgres. But here you see for the different databases, the model generalizes and can zero-shot model generalizes. So meaning, for example, if you look at the airline, if you look at the baseball case, the zero-shot model hasn't seen it and can predict good runtimes on this database out of the box. The second question is now, how does it compare to workload-driven learning? So if you give a workload-driven learning some training data on this database where you want to do the prediction, how long does it take a workload-driven model to get competitive? And we used different workload-driven models. So we used Andreas MCSM model, which was actually implemented or was designed for cardinality estimates and not runtime estimates. Therefore, maybe it's not that good in this task, but there's another model, E2E, called here from another paper, which was designed for runtime prediction. And you see, if you give this model approximately 50,000 queries, it comes or it has the same accuracy than a zero-shot model that doesn't need any training queries. But clearly, you could also say, if you anyway collect this data, so zero-shot, you could also give the zero-shot model these additional training queries for fine-tuning, and then you see that the zero-shot model is getting better. We call this way of using a zero-shot model few-shot learning, because you can start with a really good model at the beginning, and then you give it, even if you give it already 100 queries, you see that it is getting better in accuracy. So you can fine-tune this for this new database. Good. To come to the end, let me quickly go over things that I believe, why is this so, why do I really enjoy working on this direction? I think I enjoy this direction because zero-shot learning, we think this is a really general paradigm that can be used for different database tasks or components. So we just had a master thesis on the question, can we use these zero-shot cost models from materialized view selection? So the idea is we have a zero-shot model that can predict the benefits of a certain set of materialized views for a new database. So it's a variant of the cost prediction task, but you ask the question, what if a certain set of views are given? How would the runtime be for this, if these views would exist? And what you see here is that our approach, zero-shot based materialized view selection, actually provides close to optimal results. Clearly not optimal because the runtime estimates are sometimes off, but we are better than the baselines. For example, one that is based on the Postgres estimates and uses a procedure described in a Microsoft paper for view selection, or just a simple heuristic that we used for materialized view selection. Another direction is you could also ask the question, so why learn a cost model? You could also maybe learn a full optimizer in a zero-shot way. So the idea would be you have a model that can already predict query plans for a given query. And we think we can also do this in a zero-shot manner by using a similar featureization technique that I showed before that clearly needs to be adopted maybe for a query plan enumeration instead of cost prediction. Moreover, we think also that zero-shot learning is applicable beyond databases. So for example, a direction that we actually want to explore in the future is based on a work of Stratos. So he has some work on what he calls the data calculator, where the idea is that you also, given a workload characteristics and a database or data characteristics, you design an index structure from primitives such that the index is for this workload optimal. And in this design procedure, what you need to do is you need to have a cost model to decide which primitive is better. And here the cost models that are being used are at the moment pretty simple because they are just kind of calibrating the runtime for different primitives and don't really take side effects into account if you combine several primitives. And we think that a similar approach that we have now for query runtime prediction, we could also use it for predicting kind of the performance of a data structure that you assemble from different primitives. And also, since it's cost models are not only database specific, you can use this in other systems. For example, TensorFlow, one problem is device placement. So decide on which processing unit, CPU, GPU you put a tensor operation on. People have been using workload-driven approaches for that in the area of TensorFlow. And we think also zero-shot learning can be used here for deciding which tensor operation should be placed on, for example, which processing device. So overall, we believe that zero-shot is a more general paradigm for learned systems, not only databases. So with that, I think on this slide is nothing new. And in order to leave the last 4 minutes for questions, let me just stop here.